Tonight, we're going to explore one of the strangest facts in all of physics. There is a particle sitting inside every atom in your body right now, holding the nucleus together, perfectly stable, doing its job without any trouble at all. But the moment you pull that particle out, the moment it finds itself alone in empty space, it starts to die. Not in millions of years, not in thousands, in about 10 minutes. The neutron, one of the most important building blocks of matter, cannot survive on its own. Something about isolation destroys it. And the reason why is one of the most elegant and unsettling truths in all of nature. It comes down to a tiny difference in mass, so small you'd never notice it, but large enough to seal the neutron's fate. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know but have probably never thought about. Atoms. Everything around you is made of atoms. The chair you're sitting in, the air filling your lungs, the screen you're watching this on, your own body, all of it. Atoms. And at the center of almost every atom in the universe is a nucleus, a tiny dense core that contains virtually all of the atom's mass. That nucleus is built from two kinds of particles, protons and neutrons. Protons carry a positive electric charge. Neutrons carry no charge at all. That's actually where the neutron gets its name. Neutral. No charge. It's electrically invisible. If you could somehow hold a neutron in your hand, it wouldn't attract anything electrically. It wouldn't repel anything electrically. It would just sit there, neutral, silent, minding its own business. Together, protons and neutrons make up the nuclei of every element on the periodic table. Hydrogen is the simplest. Its most common form has just a single proton in its nucleus, no neutrons at all. But every other element heavier than hydrogen has neutrons in its nucleus. Helium has 2 protons and typically 2 neutrons. Carbon has 6 protons and 6 neutrons. Iron has 26 protons and 30 neutrons. Uranium has 92 protons and 146 neutrons. The pattern is clear. As atoms get heavier, they need more and more neutrons to stay together. In fact, in heavy elements, neutrons outnumber protons significantly. Without neutrons, complex matter could not exist. The periodic table would end at hydrogen. There would be no carbon, no oxygen, no iron, no gold, no uranium, no planets, no stars as we know them, no life. Neutrons are absolutely essential to the structure of matter. And here's the part that should bother you. This particle, this critical building block that holds atomic nuclei together, that makes the periodic table possible, that makes you possible, cannot survive on its own. If you take a neutron out of a nucleus and set it free in empty space, it will decay. It will fall apart. It will cease to exist as a neutron, and it won't take long. The half-life of a free neutron is about 10 minutes and 14 seconds. That means if you started with a large collection of free neutrons floating in empty space, half of them would be gone in just over 10 minutes. Not gone as in they disappeared. Gone as in they transformed into something else entirely. After another 10 minutes, half of the remaining neutrons would also have decayed. And so on, over and over, each 10-minute window, cutting the population roughly in half until eventually none of the original neutrons remain. 10 minutes. Think about how short that is. You probably spent more than 10 minutes eating your last meal. You might spend 10 minutes stuck in traffic on a short commute. In the time it takes you to brew a cup of coffee, drink half of it, and check your phone, a free neutron has a coin flip chance of having already ceased to exist. In the world of particle physics, 10 minutes is actually a remarkably long lifetime for an unstable particle. Many unstable particles decay in fractions of a second. In billionths or trillionths of a second, timescales so short that no human sense could ever register them. But the neutron lingers. It hangs around for about 10 minutes, as if it's reluctant to go, as if something about its situation is only barely unstable. And that reluctance, that slowness, turns out to be one of the most important clues about what is really going on. Now compare this to a neutron sitting inside the nucleus of, say, an iron atom. That neutron is the same particle. It has the same mass, the same internal structure, the same lack of electric charge, but that neutron inside iron's nucleus is not decaying. It's not falling apart. It's not transforming into anything. It's perfectly stable. It has been sitting there since that iron atom was forged inside a dying star billions of years ago. And it will continue sitting there for billions of years more, possibly forever. Nothing about the neutron itself has changed. It didn't become a different particle when it entered the nucleus. It didn't gain some magical protective shell. It's the same neutron, but its circumstances changed. Its environment changed. And that change in environment is the difference between stability and destruction, between existing indefinitely and falling apart in 10 minutes. This is one of the most striking facts in all of physics. Context determines survival. The same particle can be immortal in one setting and doomed in another. And the reason comes down to something so subtle, so delicate, that it almost seems like the universe is balanced on a knife's edge. But before we can understand why the neutron dies alone, we need to understand what it actually is. Not just its name, not just its role in the nucleus, but what a neutron is made of at the deepest level we currently understand. For most of the 20th century, protons and neutrons were considered fundamental particles with no internal structure. But experiments in the 1950s and 1960s revealed something unexpected. When physicists fired high-energy electrons at protons and neutrons, the electrons scattered in patterns suggesting they were bouncing off smaller objects inside. Those smaller particles were eventually called quarks, proposed independently by Murray Gell-Mann and George Feig in 1964. At first, quarks were controversial, but experiments at the Stanford Linear Accelerator Center in the late 1960s provided strong evidence they were real, revealing 3 distinct point-like objects inside each proton and neutron, each carrying a fraction of the particle's total charge and momentum. We now know that a neutron is made of 3 quarks. Specifically, it contains 1 up quark and 2 down quarks. A proton, by contrast, contains 2 up quarks and 1 down quark. That's the only difference at the quark level. 1 up quark is swapped for 1 down quark. It seems like such a minor difference, almost trivial, like changing 1 letter in a word. But that single swap changes everything. It changes the particle's electric charge, its mass, and ultimately its fate. Up quarks carry an electric charge of plus 2/3. Down quarks carry an electric charge of minus 1/3. In a proton, 2 up quarks at plus 2/3 each give plus 4/3. 1 down quark at minus 1/3 subtracts 1/3. The total is plus 4/3 minus 1/3, which equals plus 1. That's the proton's charge. Plus 1. Positive. Now do the same calculation for the neutron. 1 up quark at plus 2/3, 2 down quarks at minus 1/3 each, giving minus 2/3. The total is plus 2/3 minus 2/3, which equals 0. 0 charge, neutral. That's where the neutron gets its 0 electric charge. It's not that the neutron has no charged particles inside. It does. 3 of them. But their charges cancel out perfectly, leaving the neutron electrically invisible to the outside world. But quarks don't just float around inside the neutron like marbles in a bag. They're bound together by an extraordinarily powerful force called the strong nuclear force. This is the strongest force in nature, far stronger than gravity, far stronger than the electromagnetic force that holds electrons in orbit around nuclei. The strong force operates through the exchange of particles called gluons. Think of gluons as messengers constantly being passed back and forth between the quarks, binding them together. Except, these aren't gentle messengers. They carry enormous energy, and they interact with each other as well as with the quarks, creating a seething, chaotic environment inside the neutron. The strong force has a peculiar property called confinement. As you try to pull 2 quarks apart, The force between them doesn't weaken with distance the way gravity or electromagnetism does. Instead, it stays constant or even increases. Imagine stretching a rubber band. Eventually, if you pull hard enough, it snaps. But when the strong force snaps, the energy stored in the stretched force field creates new quarks out of pure energy. Instead of freeing the original quarks, you've created new ones. Quarks are never found alone. No one has ever observed a solitary quark floating through space. The strong force simply won't allow it. Inside the neutron, this means the quarks are trapped in an incredibly dynamic environment. The gluons that mediate the strong force carry energy, lots of it. In fact, here's something that might surprise you. The quarks inside a neutron have very little mass on their own. An up quark has a mass of only about 2.2 mega-electron-volts. A down quark has a mass of about 4.7 mega-electron-volts. If you add up the masses of one up quark and two down quarks, you get roughly 11.6 mega-electron-volts. But the neutron's total mass is about 939.565 mega-electron-volts. That means the quarks themselves account for barely more than 1% of the neutron's mass. So where does the other 99% come from? It comes from energy. The energy of the gluon field, the kinetic energy of the quarks zipping around at nearly the speed of light. The energy of the strong force interactions constantly happening inside the neutron. All of this energy contributes mass through Einstein's famous relationship between mass and energy. The neutron is, in a very real sense, almost entirely made of energy. The quarks provide the skeleton, but the strong force provides the substance. This is true for protons as well. A proton is also overwhelmingly made of energy, not quark mass. The quarks in a proton, 2 ups and 1 down, have a combined mass of about 9.4 mega-electron-volts. But the proton's total mass is about 938.272 mega-electron-volts. Again, roughly 99% of the mass comes from the energy of the strong force interactions inside. So both the neutron and the proton are fundamentally similar objects. They're both made of 3 quarks bound by gluons. They're both overwhelmingly made of energy rather than quark mass. They're both about the same size, roughly 1 femtometer across, which is 1 quadrillionth of a meter. They're practically twins. But the neutron has 1 down quark where the proton has an up quark, and that single difference gives the neutron a slightly higher mass, no electric charge, and a fundamentally different destiny when it's on its own. Now, let's talk about what happens when a free neutron decays. Because this process, called beta decay, is one of the most important transformations in all of physics. When a neutron decays, it doesn't just vanish, it transforms. It turns into 3 different particles: a proton, an electron, and a particle called an electron antineutrino. The proton carries a positive charge. The electron carries a negative charge. The antineutrino carries no charge and almost no mass. It's a ghostly particle that barely interacts with anything. It will fly off at nearly the speed of light and likely pass through the entire planet without touching a single atom. Charge is conserved in this process. The neutron started with 0 charge. The proton has +1, the electron has -1, and the antineutrino has 0. +1 minus 1 plus 0 equals 0. Everything balances. Other quantities are conserved too. The total lepton number, the total baryon number, the total energy. Nature keeps its books meticulously balanced during every transformation. But what's really happening at the quark level during beta decay is where the story gets fascinating. Remember, the neutron is made of 1 up quark and 2 down quarks. A proton is made of 2 up quarks and 1 down quark. So when a neutron turns into a proton, what has to happen is that one of the down quarks inside the neutron must change into an up quark. That's the fundamental event. 1 down quark becomes 1 up quark. The other 2 quarks, 1 up and 1 down, stay exactly as they are. They just sit there while their sibling undergoes a transformation. And when that transformation is complete, the particle that used to be a neutron with 1 up and 2 down quarks, is now a proton with 2 up quarks and 1 down quark. But a down quark can't just spontaneously become an up quark without something mediating the change. This transformation is governed not by the strong force, not by gravity, not by electromagnetism, but by the fourth and final fundamental force of nature, the weak nuclear force. The weak force is the only force in nature that can change the flavor of a quark, transforming one type of quark into another. The strong force binds quarks together but can't change what kind of quark they are. Electromagnetism affects charged particles but doesn't alter their identity. Gravity curves space-time but has no opinion about quark flavors. Only the weak force reaches into a particle and rewrites its fundamental identity. Here's how it works. The down quark inside the neutron emits a particle called a W- boson. This is one of the carrier particles of the weak force, similar to how photons carry the electromagnetic force and gluons carry the strong force. The W- boson is incredibly massive for a subatomic particle, about 80.4 gigaelectronvolts, which is roughly 86 times the mass of a proton. This extreme mass is part of why the weak force is so short-ranged and why weak interactions happen so slowly compared to strong force interactions. When the down quark emits this W- boson, it changes flavor. It becomes an up quark. The quark has changed its fundamental identity. It was a down quark carrying a charge of -1/3. Now it's an up quark carrying a charge of +2/3. The particle that contained it is no longer a neutron. It's now a proton. But the W- boson doesn't stick around. It's fantastically unstable, far more unstable than the neutron itself. It exists for an almost inconceivably brief moment, roughly 3 × 10 to the power of -25 seconds. In that fleeting instant, the W- boson decays into 2 particles, an electron and an electron antineutrino. These 2 particles fly away from the newly formed proton, carrying energy and momentum with them. The electron is the particle you might recognize from chemistry. It's what orbits the nucleus of an atom, what flows through wires as electric current, what makes chemistry and biology possible. The antineutrino is its ghostly companion, barely interacting with anything, slipping through matter as if it weren't there. And just like that, the neutron is gone. Where there was once a single neutral particle, there is now a proton, an electron, and an antineutrino flying apart. The whole process, from the perspective of the quarks inside, involved a single quark changing its identity from down to up via the weak force. 1 quark out of 3 changed, and that was enough to turn a neutron into a completely different particle. This process, beta decay, was actually observed long before anyone understood what was happening at the quark level. In the late 1800s, scientists noticed that certain radioactive materials emitted fast-moving electrons. They called these emissions beta rays, which is where the name beta decay comes from. At the time, no one knew about quarks or the weak force. They just knew that some nuclei were spitting out electrons, and no one could explain where those electrons came from. There was also a serious problem with early observations of beta decay that troubled physicists for decades. When they measured the energy of the electrons emitted during beta decay, they expected every electron to come out with the same energy. After all, if a neutron transforms into a proton and an electron, and the masses of the starting and ending particles are known, then conservation of energy should dictate exactly how much energy the electron carries. But that's not what they found. The electrons came out with a range of energies, some fast, some slow, and the total energy didn't seem to add up. Energy appeared to be disappearing. This was deeply troubling because conservation of energy is one of the most fundamental principles in all of physics. If energy wasn't conserved in beta decay, something was very wrong with our understanding of the universe. In 1930, the physicist Wolfgang Pauli proposed a daring solution. He suggested that there was a third particle being emitted during beta decay, a particle so elusive that it had escaped detection. This particle would carry away the missing energy, and its varying share of that energy would explain why the electrons came out with different energies each time. Pauli called this hypothetical particle the neutron at first, though the name was soon changed to neutrino, meaning little neutral one, after the actual neutron was discovered by James Chadwick in 1932. Enrico Fermi incorporated the neutrino into a comprehensive theory of beta decay in 1933 and 1934, creating the first mathematical framework for the weak force. More precisely, what beta decay produces is an electron antineutrino, the antimatter partner of the electron neutrino. This particle carries no electric charge, has an extraordinarily tiny mass, and interacts so weakly with ordinary matter that it can pass through a wall of lead a light year thick without being stopped. Trillions of neutrinos from the sun pass through your body every second, and you never feel a thing. The neutrino wasn't directly detected until 1956, when Clyde Cowan and Frederick Rains finally confirmed its existence using a nuclear reactor as a source. That confirmation came 26 years after Pauli first proposed it. 26 years of trusting that conservation of energy was correct, that the missing energy had to be going somewhere even though no one could find where. So here is where we stand. A free neutron, sitting alone in empty space, will decay through beta decay into a proton, an electron, and an electron antineutrino in roughly 10 minutes. This decay happens because one of the neutron's down quarks changes into an up quark through the weak force. The weak force mediates this change by producing a W- boson, which almost instantly decays into the electron and antineutrino. The proton, the electron, and the antineutrino fly apart, and the neutron is no more. But inside a nucleus, this same particle, this same neutron with the same quarks and the same internal structure, can sit undisturbed for billions of years or longer. Something about being inside the nucleus prevents the decay from happening. Something about the nuclear environment changes the rules. The question now is why? Why does isolation doom the neutron? What is it about being alone in empty space that makes decay not just possible, but inevitable? And what is it about being inside a nucleus that can shut that decay down entirely? The answer lies in something remarkably subtle. It lies in the tiniest mass difference you could imagine, a gap so small, it represents barely more than 1/10 of 1% of the neutron's total mass. But that tiny gap is everything. It is the reason free neutrons cannot survive, and understanding it will take us deep into the relationship between mass, energy, and the fundamental rules that govern which transformations nature allows and which ones it forbids. To understand why the free neutron is doomed, you need to understand one number. Just one. It's a number so small that in everyday life it would be completely meaningless. If it showed up on a bathroom scale, you'd ignore it. If it appeared as a difference in your bank account, you wouldn't even notice. But in the world of subatomic physics, this number is the difference between existence and annihilation. It is the difference between a particle that can hold itself together indefinitely and one that falls apart in minutes. That number is the mass difference between a neutron and a proton. The neutron has a mass of about 939.565 mega-electron-volts divided by the speed of light squared. The proton has a mass of about 938.272 mega-electron-volts divided by the speed of light squared. Now, if you're not familiar with these units, don't worry. Mega-electron-volts is just a unit of energy that physicists use when talking about particles, because at this scale, mass and energy are essentially the same thing. What matters is the difference between these two numbers. 939.565 minus 938.272 equals approximately 1.293 mega-electron-volts. That's the mass gap. 1.293 mega-electron-volts. That's about 0.14% of the neutron's total mass. If the neutron were a person weighing 150 pounds, This difference would be about 3.5 ounces. You would never notice it. You couldn't feel it. It would be completely lost in the noise of daily fluctuations. And yet, this tiny sliver of extra mass is the entire reason a free neutron cannot survive. To understand why, you need to understand perhaps the most famous equation in all of science: E equals mc squared. Einstein published this relationship in 1905 as part of his special theory of relativity. The equation says that energy and mass are two forms of the same thing. They're interconvertible. Mass can become energy, and energy can become mass. The c squared part is just the exchange rate between the two. And because the speed of light is enormous, a tiny amount of mass corresponds to a huge amount of energy. This is why nuclear weapons are so powerful. They convert a small fraction of their mass into energy, and that small fraction, multiplied by the speed of light squared, produces an explosion capable of leveling a city. But Einstein's equation works in both directions. Not only can mass become energy, but energy can become mass. When two particles collide at extremely high speeds in a particle accelerator, their kinetic energy can be converted into entirely new particles that didn't exist before. The mass of those new particles comes directly from the energy of the collision. This isn't metaphor. It's not a convenient way of talking. It's literal physical reality. Mass and energy are the same fundamental quantity expressed in different forms. Now, here's why this matters for the neutron. In nature, transformations between particles are governed by strict rules. One of the most important rules is conservation of energy. The total energy before a process must equal the total energy after. Energy cannot be created from nothing, and it cannot simply vanish. It can change form. It can move from one place to another, but the total amount must remain the same. Because mass is a form of energy, this means that the total mass energy before a decay must equal the total mass energy after. If a particle decays into lighter products, the leftover mass energy has to go somewhere. It becomes kinetic energy, the energy of motion carried away by the decay products. But if a particle were to try to decay into heavier products, it would need extra energy from somewhere. And for a particle sitting alone in empty space with no external energy source, that extra energy simply isn't available. The decay is forbidden. Not just unlikely, forbidden. The laws of physics will not allow it. This is where the neutron's fate is sealed. The neutron is heavier than the proton. That 1.293 megaelectronvolts of extra mass means the neutron has more mass energy than the proton. So when a neutron decays into a proton, the mass side of the equation goes down. There's mass energy left over, but the neutron doesn't just decay into a proton. It decays into a proton, an electron, and an electron antineutrino. So we need to check whether the neutron is heavier than all three of these products combined. The proton has a mass of 938.272 megaelectronvolts. The electron has a mass of about 0.511 megaelectronvolts. The electron antineutrino has a mass so tiny that for this purpose it's essentially zero. Recent measurements suggest neutrino masses are less than 1 electron volt, which is 1,000,000 times smaller than a megaelectronvolt. So for this calculation, we can safely treat it as zero. Adding up the products gives us 938.272 plus 0.511, which equals approximately 938.783 megaelectronvolts. Now compare that to the neutron's mass of 939.565 megaelectronvolts. The neutron is heavier than its decay products by about 0.782 megaelectronvolts. That's the leftover. That's the surplus mass energy that gets converted into kinetic energy and carried away by the decay products when the neutron falls apart. And that surplus is everything. It's the reason the decay is allowed. It's the reason a free neutron is unstable. If the neutron were lighter than the combined mass of its decay products, beta decay would be energetically impossible. The neutron would just sit there, alone in space, unable to transform because nature doesn't permit transformations that require creating energy from nothing. But because the neutron is heavier, even by this tiny amount, the decay is not just possible, it's inevitable. Given enough time, a free neutron will always decay. The surplus mass energy means there's a downhill path, an energetically favorable transition from neutron to proton, plus electron, plus antineutrino. And in physics, anything that can happen eventually will. Let me try to make this more concrete with an analogy. Imagine a boulder sitting at the top of a hill. If there's a valley below, the boulder can roll down. Gravity will pull it. It might take a long time, there might be friction, there might be obstacles, but eventually if the valley is lower than the hilltop, the boulder will find its way down. The difference in height between the hilltop and the valley floor is what makes the roll possible. Now imagine the boulder is sitting at the bottom of the valley. There's no lower point to roll to. It just stays put. No amount of weighting will cause it to spontaneously roll uphill, because that would require adding energy. The free neutron is like a boulder on a hilltop. The proton plus electron plus antineutrino combination is like the valley floor. The mass difference, that 1.293 mega electron volts, is like the height of the hill. It's what makes the downhill roll possible. The neutron will eventually roll down that hill, transforming into lighter products and releasing the surplus energy as kinetic energy. But here's the thing about that analogy. A real boulder on a real hill would roll down almost immediately. Gravity would pull it, and within seconds it would be at the bottom. The free neutron, by contrast, takes about 10 minutes on average. In the subatomic world, 10 minutes is an eternity. Most particle decays happen in tiny fractions of a second. Pions, which are particles that help mediate the strong force inside atomic nuclei, have lifetimes measured in billionths of a second. Some particles decay in trillionths of a second. Even some particles with much larger mass differences between themselves and their decay products decay far faster than the neutron does. So why is the neutron so slow? The answer is that the decay is mediated by the weak nuclear force, and the weak force is genuinely weak. Its name is not just a label, it describes a real physical property. The weak force is vastly feebler than the strong force and the electromagnetic force. It's called weak because the probability of a weak interaction happening at any given moment is extremely small, compared to the probability of a strong or electromagnetic interaction. The strong force operates on timescales of about 10 to the power of negative 23 seconds. That's almost instantaneous. The electromagnetic force operates on timescales of about 10 to the power of negative 16 to negative 20 seconds. Still incredibly fast. But the weak force operates on timescales that can range from 10 to the power of negative 13 seconds all the way up to minutes, years, or even billions of years, depending on the specific decay and how much energy is available. The reason the weak force is so feeble comes back to those W bosons we talked about earlier. Remember, when a down quark inside the neutron changes into an up quark, it does so by emitting a W- boson. But the W boson is extremely heavy, about 80.4 gigaelectronvolts, which is roughly 86 times the mass of a proton. This massive particle must briefly exist during the decay process, even though there isn't nearly enough energy available to create it as a real, permanent particle. The neutron's entire mass energy is only about 940 megaelectronvolts, far less than the 80,400 megaelectronvolts needed to create a real W boson. So how does the decay happen at all? Through a quantum mechanical phenomenon. The W boson exists as what physicists call a virtual particle. In quantum mechanics, particles can briefly borrow energy from the vacuum, creating particles that shouldn't be able to exist given the available energy, as long as they give that energy back quickly enough. This is connected to Heisenberg's uncertainty principle, which says that energy and time are linked by a fundamental trade-off. The more energy you borrow, the shorter the time you can borrow it for. Since the W boson requires an enormous amount of borrowed energy, roughly 80,000 megaelectronvolts more than the neutron has, it can only exist for an extraordinarily brief time. This brief existence severely suppresses the probability of the decay. It makes the interaction extremely unlikely at any given instant. That's why the neutron hangs on for 10 minutes instead of decaying in a fraction of a second. The weak force is trying to make the decay happen, but the extreme mass of the W boson makes each attempt very unlikely to succeed. It's like trying to push a boulder through a wall. Most attempts fail. Occasionally, quantum mechanics allows one to succeed, and so the neutron waits, each moment carrying a tiny probability of decay, until eventually the decay occurs. Now, let's talk about what happens to the surplus energy when the neutron actually decays. The mass difference between the neutron and its decay products is about 0.782 mega electron volts. This energy must go somewhere because energy is conserved. It goes into the kinetic energy of the decay products, the proton, the electron, and the antineutrino. They fly apart, each carrying a share of this energy, but the shares aren't fixed. This is the fascinating part. Each time a neutron decays, the energy is divided differently among the three products. Sometimes the electron gets most of the energy and comes out moving fast. Sometimes the antineutrino gets most of the energy. Sometimes the energy is divided more evenly. This randomness is fundamental. It's built into quantum mechanics. You can't predict exactly how the energy will be divided for any individual neutron decay. You can only predict the statistical distribution over many decays. This variable energy sharing was the very clue that led to the neutrino's prediction in the first place. Before Pauli proposed it, the electron seemed to come out with random amounts of energy, and the total didn't add up. The crisis was so severe that some of the greatest minds in physics, including Niels Bohr himself, seriously considered the possibility that conservation of energy simply didn't apply at the subatomic level. That would have been a revolutionary and deeply unsettling conclusion, overturning one of the most foundational principles in all of science. Pauli's insight that a third unseen particle was carrying away the missing energy rescued conservation of energy from the brink. The total always balanced. It just took 26 years to prove that the invisible partner was real. Let's pause here and really absorb how delicate this entire situation is. The neutron is heavier than the proton by 1.293 mega electron volts, but the neutron's total mass is about 939.565 mega electron volts. That mass difference is about 0.14% of the total. Imagine you had a bank account with $939,565 in it, and someone told you that your financial future hinged on whether or not you had an extra $1,293. That's what we're talking about. A sliver, a razor-thin margin. And yet this margin determines whether a particle lives or dies. Now, think about what would happen if the situation were reversed. What if the proton were heavier than the neutron instead of the other way around? If the proton had more mass energy than the neutron, then the decay would go in the opposite direction. Protons would decay into neutrons, positrons, which are the antimatter counterparts of electrons, and neutrinos. And free protons would be the unstable ones, falling apart in minutes, while free neutrons would be perfectly stable. This isn't just a thought experiment. The direction of this decay is entirely determined by which particle is heavier. Nature doesn't care about labels. It doesn't care that we call one a proton and the other a neutron. It only cares about mass energy. The heavier particle can decay into the lighter one. The lighter one cannot decay into the heavier one without an external energy source. Full stop. That's the rule. And if protons were unstable, the consequences for the universe would be catastrophic. Hydrogen, the most abundant element in the universe, has a nucleus that's just a single proton. If protons decayed in 10 minutes, hydrogen couldn't exist. Without hydrogen, there would be no water, no stars powered by hydrogen fusion, no organic chemistry. The universe as we know it would be completely impossible. The fact that the proton is slightly lighter than the neutron, and therefore stable, is one of the most fortunate accidents in all of physics. Or maybe it's not an accident at all. Maybe it's a necessary condition for any universe that contains observers capable of asking these questions. But that's a philosophical debate, not a physics one. The mass difference between the neutron and the proton seems like it should be simple to explain. After all, the only difference between them at the quark level is that the neutron has 2 down quarks and 1 up quark, while the proton has 2 up quarks and 1 down quark. So you might think the mass difference just comes from the difference in quark masses. An up quark has a mass of about 2.2 mega electron volts. A down quark has a mass of about 4.7 mega electron volts. The neutron has 1 up and 2 down quarks, giving a total quark mass of about 2.2 plus 4.7 plus 4.7, which equals 11.6 mega electron volts. The proton has 2 up and 1 down quark, giving a total quark mass of about 2.2 plus 2.2 plus 4.7, which equals 9.1 mega electron volts. The difference in quark mass between neutron and proton is about 2.5 mega electron volts, with the neutron being heavier. But wait, the actual mass difference between the neutron and the proton is only 1.293 mega electron volts, not 2.5. So something else must be partially compensating for the quark mass difference, making the neutron not quite as heavy relative to the proton as the quark masses alone would suggest. That something is electromagnetic energy. The proton has a positive electric charge, and the quarks inside it are arranged in a way that creates electromagnetic self-energy. The electrostatic repulsion between the positively charged quarks inside the proton adds to its mass energy. The neutron, being neutral overall, has less electromagnetic self-energy. This electromagnetic contribution partially offsets the quark mass difference, bringing the actual neutron-proton mass difference down from what quark masses alone would predict. The fact that the final answer, 1.293 mega electron volts, is a small difference between 2 much larger competing effects. The quark mass difference pulling one way and the electromagnetic energy pulling the other makes this number seem almost accidental. It's not determined by any single clean mechanism. It's the result of a delicate tug-of-war between different physical effects that happen to nearly cancel out, leaving a tiny residual. Change the up quark mass by a tiny amount, or the down quark mass, or the strength of the electromagnetic force, and this number shifts. Make it a little bigger, and neutrons decay faster. Make it a little smaller, or reverse the sign entirely, and the universe as we know it ceases to exist. This sensitivity has profound implications for understanding why the universe looks the way it does. The mass difference between the neutron and the proton is set by the fundamental constants of nature, the quark masses and the strength of the electromagnetic and strong forces. These constants appear to be finely tuned in a way that allows complex matter to exist. If the down quark were just slightly lighter or the up quark slightly heavier, the proton could end up heavier than the neutron. Protons would be unstable, hydrogen wouldn't exist, and the entire chemical foundation of the universe would collapse. If the mass difference were much larger in the other direction, with the neutron being far heavier than the proton, then neutrons would decay so quickly that they might not survive long enough to be captured into nuclei during the first few minutes after the Big Bang. Without neutrons in nuclei, you couldn't build helium, carbon, oxygen, or any element beyond hydrogen. Again, the universe would be a very different and far simpler place. The mass difference we actually have, 1.293 mega electron volts, sits in a remarkably narrow sweet spot. It's large enough that free neutrons decay on a timescale of minutes, which is slow enough that during the Big Bang nucleosynthesis period, the first few minutes after the Big Bang, many neutrons survived long enough to be captured into helium nuclei before they could decay. This is why the universe ended up with roughly 25% helium by mass. If neutrons decayed much faster, almost all of them would have decayed before they could be captured, and the universe would be almost entirely hydrogen. If they decayed much slower, more neutrons would have survived, and the universe would have more helium and potentially heavier elements from the start. The particular timescale of a neutron decay, set by this mass difference and by the strength of the weak force, determine the chemical composition of the early universe. Your existence depends on it. Here's another way to think about how precise this balance is. The neutron's total mass is about 939.565 mega electron volts. The mass difference that makes it unstable is about 1.293 mega electron volts. If you scaled the neutron's mass to the height of a 300-story skyscraper, roughly 1,000 meters tall, the mass difference that determines whether it lives or dies would correspond to about 1.4 meters, about the height of a child. The entire fate of the neutron, the reason it cannot survive alone, is determined by a margin that's like one child's height compared to a skyscraper. Everything else, the 938 plus mega electron volts of mass energy from the strong force, from the kinetic energy of quarks, from the gluon field, all of that is shared between neutron and proton almost identically. The overwhelming majority of both particles is the same seething soup of quarks and gluons generating mass from energy. But at the very end of the calculation, after all the enormous numbers have been added up and nearly cancelled out, there's this tiny residual. And that residual points in one direction rather than the other. The neutron is just barely heavier than the proton. And barely heavier means unstable. There's something almost philosophical about this. The neutron doesn't decay because it's fundamentally different from the proton. It doesn't decay because it's made of some exotic unstable material. It doesn't decay because there's something wrong with it. It decays because it has a tiny bit of extra mass, and nature will always seek the lowest energy state available. The neutron is like water on a slope. It doesn't matter how gentle the slope is. It doesn't matter if the incline is almost imperceptible. Given enough time, water flows downhill. The free neutron flows downhill too. From its slightly higher mass state to the slightly lower mass state of a proton plus electron plus antineutrino. The slope is gentle, barely there, which is why the process takes 10 minutes instead of a fraction of a second. But it's there. And as long as it's there, the neutron cannot resist. It will eventually transform. This brings us to a deeper principle that governs all particle physics, and indeed, all of nature. Systems tend toward their lowest available energy state. A ball rolls to the bottom of a bowl, hot objects cool down, stretched rubber bands contract, unstable particles decay into lighter ones. This isn't just a tendency. In quantum mechanics, it's essentially a mathematical certainty given enough time. If there exists a lower energy configuration that a system can reach through any physically allowed process, it will eventually reach it. The only question is how long it takes. For the free neutron, the lower energy configuration exists. It's the proton plus electron plus antineutrino state. The physically allowed process exists. It's beta decay via the weak force. And the time it takes is about 10 minutes, set by the feebleness of the weak force and the extreme mass of the virtual W boson that mediates the interaction. But here's the crucial twist that leads us toward understanding why neutrons inside nuclei can be stable. Everything I've just said applies to a neutron that is alone. A neutron floating in empty space with nothing around it. In that situation, the neutron has one choice. It can stay as it is, or it can decay into a proton, electron, and antineutrino. Staying as it is means keeping its higher mass energy. Decaying means dropping to a lower mass energy. The choice is clear. The decay wins. But what happens when a neutron is not alone? What happens when it's surrounded by other protons and neutrons inside an atomic nucleus? What happens when there are other forces at play, other energies involved, other quantum mechanical rules constraining what's allowed? In that case, the simple accounting of mass energy gets more complicated, much more complicated, because now the neutron doesn't exist as an isolated particle. It exists as part of a system. And the relevant question is no longer whether the neutron alone is heavier than its decay products. The relevant question becomes whether the entire system, nucleus and all, would have lower or higher energy after the decay. And that's a completely different calculation. Inside a nucleus, the neutron is bound to other particles by the strong force. That binding releases energy, and by Einstein's equation, released energy means reduced mass. The bound system actually weighs less than its individual components would if you separated them. This missing mass, called the mass defect, is the binding energy of the nucleus converted into mass units. Breaking the nucleus apart would require adding energy equal to the binding energy. This is why nuclei are stable. They're sitting in an energy well, a valley. Getting out requires climbing uphill. When a neutron inside a nucleus considers decaying, it's not just transforming into a proton and releasing an electron and antineutrino. It would be transforming the entire nucleus from one element to another. The nucleus would go from having a certain number of protons and neutrons to having one more proton and one fewer neutron. This new nucleus has different binding energy, different electromagnetic energy from the repulsion between its protons, different quantum mechanical energy from the arrangement of particles in nuclear energy levels. The total energy of the system after the decay might be higher than the total energy before the decay. And if it's higher, the decay is forbidden. The neutron cannot decay because doing so would require the system to go uphill energetically. And there's no external energy source to make that happen. The neutron is trapped in a stable configuration, held in place not by any physical barrier but by the arithmetic of energy. This is the resolution of the paradox. The free neutron decays because it sits at a higher energy than its decay products, and nothing prevents it from rolling downhill. The bound neutron in a stable nucleus doesn't decay because the nuclear environment changes the energy landscape. The hill disappears. In fact, in many stable nuclei, the situation is reversed. The bound neutron sits in a valley. Decaying would mean going uphill, and uphill transformations don't happen spontaneously. They're forbidden by conservation of energy. It's the same neutron, the same quarks, the same internal structure, but its surroundings, its context within a nuclear system, completely change whether the decay is energetically possible. The neutron doesn't know it's in a nucleus in any conscious sense, but the laws of physics know, the energy accounting knows, and that accounting determines everything. This is perhaps one of the most beautiful examples in all of physics of how context determines fate. The neutron is not inherently unstable. It's not inherently stable either. It's conditionally unstable. Its stability depends entirely on where it is and what surrounds it. Alone, it decays. Bound in certain nuclei, it endures. And the reason comes down to nothing more than a careful comparison of total energies before and after the potential transformation. The universe doesn't play favorites. It doesn't protect neutrons or doom them. It simply follows the rules of energy conservation with absolute precision. And those rules say that a free neutron, carrying its tiny surplus of mass compared to its potential decay products, has no choice but to eventually transform. The slope is gentle, the process is slow, but the outcome is certain. A free neutron cannot survive. Not because it's broken, not because it's flawed, but because the mathematics of mass and energy leave it no other option. So we've established the fundamental rule. A free neutron decays because it's heavier than its decay products, and nature permits any transformation that moves downhill in energy. But now we need to confront the obvious question that makes this story so much more interesting. If neutrons are inherently unstable, if they carry this tiny surplus of mass that dooms them in empty space, then why don't all neutrons everywhere decay? Why is the universe full of stable neutrons sitting contentedly inside atomic nuclei, some of them billions of years old, showing no signs of decay whatsoever? The answer takes us into the heart of nuclear physics, into the energy landscape of the atomic nucleus, where the simple arithmetic of a single particle's mass gives way to something far more intricate. Inside a nucleus, The question is no longer whether a neutron is heavier than a proton. The question becomes whether the entire nucleus would be lighter or heavier after the transformation. And that question has a completely different answer, depending on which nucleus you're talking about. Let's start with the most basic concept: binding energy. When protons and neutrons come together to form a nucleus, they don't just stack up like bricks. They bind to each other through the strong nuclear force, and that binding releases energy. This is a crucial point. When particles bind together, the system loses energy. And because mass and energy are equivalent, that lost energy means the bound system has less mass than the individual particles would have if they were all separated. This difference is called the mass defect, and it represents the binding energy of the nucleus expressed in mass units. The more tightly bound a nucleus is, the larger its mass defect, and the more energy you would need to supply to tear it apart. Consider the simplest nucleus that contains a neutron: deuterium, also called heavy hydrogen, with one proton and one neutron bound together. If you add the masses of a free proton and a free neutron, you get about 1,877.837 mega electron volts. But the actual mass of a deuterium nucleus is about 1,875.613 mega electron volts. That's less than the sum of its parts by about 2.224 mega electron volts. That missing mass is the binding energy, released when the proton and neutron came together, carried away as a gamma ray or as kinetic energy. To break the deuterium nucleus back apart into a free proton and a free neutron, you would need to supply that same 2.224 mega electron volts. It's like a ball that has fallen into a hole. To get the ball out, you need to supply enough energy to lift it back up to ground level. Now, here's where this matters for neutron decay. Suppose the neutron inside deuterium wanted to undergo beta decay. It would transform into a proton, emitting an electron and an antineutrino. But what would the result look like? The deuterium nucleus currently has one proton and one neutron. If the neutron decays, you'd be left with 2 protons and 0 neutrons. 2 protons sitting next to each other form a nucleus called diproton, or helium-2. But here's the problem. 2 protons sitting right next to each other repel each other electromagnetically. They're both positively charged, and like charges repel. The strong force tries to hold them together, but for just 2 protons without any neutrons to help stabilize the system, the electromagnetic repulsion overwhelms the strong force's attraction at this particular configuration. Helium-2 is not a bound system. It doesn't exist as a stable nucleus. The 2 protons would immediately fly apart. So the end result of the neutron's attempted decay inside deuterium would be 2 free protons plus an electron plus an antineutrino. We need to compare the total mass energy of this final state with the total mass energy of the initial state, the deuterium nucleus. The deuterium nucleus has a mass of about 1,875.613 mega electron volts. 2 free protons would have a combined mass of about 1,876.544 mega electron volts. Just the 2 protons alone already weigh more than the deuterium nucleus, even before you add the mass of the electron. The final state is heavier than the initial state. The decay would have to go uphill energetically, and that's forbidden. Conservation of energy says no. The neutron inside deuterium cannot decay, because doing so would require creating mass energy from nothing. The binding energy of the deuterium nucleus has changed the energy landscape so dramatically that the decay path that was open for a free neutron is now blocked. The slope that existed for the free neutron has been inverted. Instead of rolling downhill, the neutron would have to roll uphill, and spontaneous uphill transformations don't happen. This is the essential mechanism. The nuclear binding energy effectively changes the mass-energy balance of the decay equation. For a free neutron, the products of decay are lighter than the neutron, so decay proceeds. For a neutron inside deuterium, the products of decay, which now include the breakup of the nucleus, are heavier than the original system, so decay is blocked. Same neutron, same quarks inside, same weak force available, but the energy arithmetic has flipped, and that flip makes all the difference. Let's extend this thinking to heavier nuclei, because the principle becomes even more powerful. Consider helium-4, also known as an alpha particle. This nucleus has 2 protons and 2 neutrons, and it's extraordinarily tightly bound. The binding energy of helium-4 is about 28.3 mega-electron volts. That's a lot of binding energy for just 4 particles. This makes helium-4 one of the most stable nuclei in existence. Now, imagine one of the neutrons inside helium-4 trying to decay. The neutron would become a proton, giving you a nucleus with 3 protons and 1 neutron, plus the emitted electron and antineutrino. A nucleus with 3 protons and 1 neutron would be lithium-4. But lithium-4 is extremely unstable. It falls apart almost instantly, because that particular combination of protons and neutrons doesn't form a well-bound system. The energy you'd need to rearrange the nucleus from helium-4's beautifully stable configuration into the unstable mess of lithium-5 far exceeds the 1.293 mega-electron volts of mass difference between a neutron and proton. The nuclear binding energy has built such a deep energy well around the neutron that the tiny mass energy surplus that drives free neutron decay is completely irrelevant. It's like a pebble trying to roll out of the Grand Canyon. The pebble might sit on a very slight local slope, but the canyon walls tower far above it. It isn't going anywhere. Iron 56 is often cited as one of the most tightly bound nuclei per nucleon. It has 26 protons and 30 neutrons, and its binding energy per particle is about 8.8 mega-electron volts. Every neutron and proton inside Iron 56 is sitting in a deep energy well. The idea that one of those neutrons could decay, rearranging the entire nuclear energy structure by converting Iron 56 into cobalt 56, is energetically forbidden. The cobalt 56 nucleus that would result is less tightly bound than the Iron 56 starting point. The total mass energy of the system would increase, not decrease. The decay cannot happen. Those neutrons inside Iron 56 have been sitting there since the iron was forged in the core of a massive star that exploded as a supernova billions of years ago. They will sit there effectively forever, as stable as any particle in the universe. But now we need to introduce something critical to understanding why nuclear stability isn't just about binding energy alone. It's also about quantum mechanics, specifically a rule called the Pauli exclusion principle. This principle, formulated by the physicist Wolfgang Pauli in 1925, says that no 2 identical fermions can occupy the same quantum state simultaneously. Protons are fermions, neutrons are fermions, electrons are fermions. The Pauli exclusion principle applies to all of them. Inside a nucleus, this means that protons and neutrons must occupy distinct quantum states. Think of it like an apartment building where each apartment can hold at most 1 proton or 1 neutron. Actually, because protons and neutrons are different particles, they have their own separate apartment buildings. Protons fill up proton energy levels, and neutrons fill up neutron energy levels. The lowest energy levels get filled first, then higher ones, just like water filling a container from the bottom up. This arrangement of particles into energy levels creates what physicists call the nuclear shell structure, somewhat analogous to the electron shell structure that governs chemistry. Certain numbers of protons or neutrons fill complete shells, creating particularly stable configurations. These special numbers, 2, 8, 20, 28, 50, 82, and 126, are called magic numbers. Nuclei with magic numbers of protons or neutrons, or both, are exceptionally stable. Helium-4 has 2 protons and 2 neutrons, both magic numbers, which is part of why it's so tightly bound. Oxygen-16 has 8 protons and 8 neutrons, both magic. Calcium-40 has 20 protons and 20 neutrons, both magic. Lead-208 has 82 protons and 126 neutrons, both magic, making it the heaviest stable nucleus with a doubly magic configuration. The Pauli exclusion principle matters for neutron decay inside nuclei because when a neutron decays into a proton, the new proton must go somewhere. It must occupy an available proton energy level. But if all the low energy proton levels are already filled, the new proton would have to go into a higher energy level. Occupying a higher energy level means having more energy, and that additional energy might be enough to make the overall decay energetically unfavorable. Even in cases where the simple mass difference between neutron and proton would otherwise allow it, the new proton can't squeeze into a level that's already taken. It must go to the next available level, and if that level is high enough in energy, the total cost of the transition exceeds the mass energy surplus. The decay is blocked. The neutron survives. This is particularly important in nuclei that have many more protons than neutrons. In such nuclei, the proton energy levels are filled up to a high level, leaving no low energy vacancies for a new proton. A neutron trying to decay would produce a proton that has nowhere to go except a high energy state, making the whole process energetically impossible. The Pauli exclusion principle acts as a gatekeeper, preventing the creation of protons that have no available quantum state to occupy at a sufficiently low energy. The reverse situation is also interesting. In nuclei with many more neutrons than protons, the neutron energy levels are filled up to a high level, while the proton energy levels have vacancies at lower energies. In these nuclei, a neutron sitting in a high energy neutron level can decay into a proton that drops into a lower energy proton level, and the energy released by the proton dropping to a lower level can more than compensate for the neutron-proton mass difference. The decay becomes energetically favorable. These nuclei are unstable. They undergo beta decay, with neutrons converting to protons, emitting electrons and antineutrinos, until the nucleus reaches a more balanced configuration, where the energies of the highest occupied proton and neutron levels are roughly equal. This is exactly what happens in radioactive isotopes. The reason certain isotopes are radioactive and others are stable is precisely this energy accounting. It's not random. It's not mysterious. It's a straightforward consequence of comparing the total energy of the system before and after a potential decay. If a nucleus has too many neutrons for its number of protons, the neutron energy levels are filled up to a high point while proton levels have lower energy vacancies available. Beta decay is energetically favorable. The nucleus is radioactive. It will emit electrons and antineutrinos as neutrons convert to protons, shifting the neutron to proton ratio toward a more stable balance. If a nucleus has too many protons for its number of neutrons, the opposite process can occur. A proton can convert to a neutron, emitting a positron and a neutrino. This is called beta plus decay, or positron emission. The proton energy levels are filled up too high while neutron levels have lower energy vacancies. The proton drops to a lower energy by becoming a neutron. And if a nucleus has just the right ratio of neutrons to protons, sitting in the energy valley where neither decay direction is energetically favorable, the nucleus is stable. No beta decay occurs. The neutrons and protons sit in their respective energy levels, perfectly balanced, indefinitely. The valley of stability is a term physicists use to describe this balance. If you make a chart of all known nuclei, plotting the number of protons on one axis and the number of neutrons on the other, and then color-coding each nucleus by its stability, a pattern emerges. Stable nuclei cluster along a curved band, the valley of stability, where the neutron-to-proton ratio is just right. For light elements, the ratio is close to 1:1. Carbon-12 has 6 protons and 6 neutrons. Oxygen-16 has 8 of each. But as elements get heavier, stable nuclei need more neutrons than protons. Iron-56 has 26 protons but 30 neutrons. Gold, 197, has 79 protons, but 118 neutrons. Lead 208 has 82 protons, but 126 neutrons. The reason heavier elements need proportionally more neutrons is the electromagnetic force. As you add more protons to a nucleus, the electromagnetic repulsion between them grows. Each proton repels every other proton. For a nucleus with 80 protons, the total electromagnetic repulsion is enormous. To counterbalance this, you need extra neutrons. Neutrons contribute to the strong force attraction without adding to the electromagnetic repulsion because they have no charge. Extra neutrons act as nuclear glue, adding strong force binding without electromagnetic cost, helping to stabilize nuclei that would otherwise be torn apart by the mutual repulsion of their protons. Nuclei that sit above the valley of stability with too many neutrons undergo beta- decay. Neutrons transform into protons, moving the nucleus back toward the valley. Nuclei that sit below the valley with too many protons undergo beta plus decay or electron capture. Protons transform into neutrons, again moving the nucleus toward the valley. The valley of stability is like a riverbed, and unstable nuclei are like raindrops falling on the hillsides. No matter where they land, they flow downhill toward the river. The valley represents the configuration of minimum energy, the arrangement where the competing forces of strong attraction, electromagnetic repulsion, and the quantum mechanical constraints of the Pauli exclusion principle all reach a balance. Let me give you a specific example to make this concrete. Consider carbon-14, the isotope used in radiocarbon dating. Carbon-14 has 6 protons and 8 neutrons. Stable carbon, carbon-12, has 6 protons and 6 neutrons. Carbon-14 has 2 extra neutrons. Those extra neutrons push the neutron energy level slightly higher than they need to be for optimal stability. The nucleus is sitting on the slope above the valley, and beta decay is energetically favorable. One of the neutrons in carbon-14 can transform into a proton, producing nitrogen-14, which has 7 protons and 7 neutrons. Nitrogen-14 sits right in the valley of stability. The decay releases energy because the final state, nitrogen-14 plus an electron plus an antineutrino, has less total mass energy than the initial state. Carbon-14, but carbon-14 decays slowly. Its half-life is about 5,730 years. Compare this to the free neutron's half-life of 10 minutes. Same type of decay, beta minus, same weak force, same W boson mediating the process. So why is carbon-14 so vastly more long-lived than a free neutron? The answer begins with the energy available for the decay. The free neutron's decay releases about 0.782 megaelectronvolts of kinetic energy. Carbon-14's decay releases only about 0.156 megaelectronvolts. That's about 5 times less energy. In beta decay, the rate of decay is extremely sensitive to the available energy. A smaller energy release means the decay happens much more slowly. The relationship isn't linear. It follows a steep power law. Roughly speaking, the decay rate scales as the 5th power of the available energy for low-energy beta decays. Cutting the available energy by a factor of 5 can slow the decay by a factor of several thousand from that effect alone. But the full picture includes additional factors specific to each nucleus, including the detailed quantum mechanical structure of the initial and final nuclear states, and how strongly they overlap. These nuclear structure effects, combined with the energy sensitivity, compound together to produce the enormous range of half-lives observed in beta-decaying nuclei. Some neutron-rich nuclei decay in fractions of a second because the energy difference is large. Others, like carbon-14, decay over thousands of years because the energy difference is small. And some nuclei don't decay at all because the energy difference is 0 or negative, meaning the decay is forbidden entirely. Tritium is another excellent example. Tritium is hydrogen-3, with 1 proton and 2 neutrons. It's the heaviest isotope of hydrogen. Tritium undergoes beta decay, with one of its neutrons transforming into a proton, producing helium-3, which has 2 protons and 1 neutron. The half-life of tritium is about 12.32 years. The energy released in this decay is only about 0.0186 mega-electron volts. That's tiny. It's one of the lowest energy beta decays known for any isotope that decays. Because the energy is so small, the decay is very slow by nuclear standards. 12 years might not sound slow in human terms, but for a nuclear decay, it's quite leisurely. And the reason it happens at all is that tritium, with its 2 neutrons and 1 proton, sits slightly above the valley of stability. Helium-3, with 2 protons and 1 neutron, sits slightly lower in energy. The slope is gentle, almost flat, so the decay is slow. But the slope is there, so the decay happens. Now, let's consider what happens at the extreme end of the periodic table. Very heavy nuclei, those with more than about 83 protons, are all unstable. Every isotope of every element beyond bismuth is radioactive. The reason is that the electromagnetic repulsion between so many protons eventually overwhelms the strong force, even with a large surplus of neutrons. These nuclei sit on a hilltop with no stable valley to occupy. They decay through various processes, including beta decay, alpha decay, where the nucleus emits a helium-4 particle, and in extreme cases, spontaneous fission, where the nucleus literally splits in two. Uranium-238, with 92 protons and 146 neutrons, has a half-life of about 4.5 billion years. That's comparable to the age of the Earth. It decays primarily through alpha emission, shedding protons and neutrons 2 at a time, gradually working its way down to lead, which is stable. The neutrons inside uranium-238 aren't undergoing beta decay because the energy balance within uranium's nuclear structure doesn't favor that particular transition. Instead, the whole nucleus sheds alpha particles, which is a different mechanism driven by the overall instability of having so many protons packed together. The story of nuclear stability is ultimately a story about energy landscapes. Every nucleus sits at some point on a vast multidimensional energy surface. The axes of this surface include the number of protons, the number of neutrons, and various quantum mechanical properties of the nuclear configuration. Stable nuclei sit at local minima on this surface, valleys from which no energetically downhill transformation is available. Unstable nuclei sit on slopes or hilltops where one or more downhill paths exist. Beta decay, alpha decay, gamma emission, and fission are all different pathways down different slopes on this surface. A nucleus will take whatever path is available that leads downhill. For neutrons specifically, the key insight is this: the free neutron sits on a gentle slope. Its decay products are slightly lighter, so it rolls slowly downhill over the course of about 10 minutes. But when a neutron is incorporated into a nucleus, the energy surface changes completely. The neutron is no longer sitting on a slope. It might be sitting in a deep valley. The transformation that was available to it as a free particle, beta decay into a proton, electron, and antineutrino, is no longer necessarily downhill. The strong force-binding energy, the electromagnetic energy of the proton arrangement, and the Pauli exclusion principle all reshape the energy surface around the neutron, potentially eliminating the downhill path entirely. In stable nuclei, the path is eliminated. The neutron cannot decay because all possible final states have higher energy than the current state. In unstable neutron-rich nuclei, the path still exists, but it might be gentler or steeper than the free neutron's path, leading to half-lives that range from milliseconds to billions of years depending on the specific energy difference. The nucleus is like a complex terrain. Some neutrons sit in deep valleys, others sit on gentle slopes, others sit on steep cliffs. Their fate depends entirely on the local topography of the energy surface. This understanding also explains why nuclear reactions can release or absorb energy. When light nuclei fuse together as happens in the core of a star, the resulting heavier nucleus can be more tightly bound per particle than the original nuclei. The mass of the fusion product is less than the combined mass of the starting nuclei. The difference in mass is released as energy. This is what powers the sun. Hydrogen nuclei fuse into helium, and the helium nucleus is more tightly bound per particle than the individual hydrogen nuclei were. The mass deficit is converted into radiation and kinetic energy, producing the sunlight and heat that sustain life on Earth. Conversely, when very heavy nuclei split apart through fission, the resulting fragments are more tightly bound per particle than the original heavy nucleus. Again, mass is lost and energy is released. This is what powers nuclear reactors and nuclear weapons. Both fusion and fission release energy because they move nuclei closer to the peak of the binding energy curve, closer to iron 56, where nuclei are most tightly bound per particle. In both cases, neutrons play a critical role. Fusion of hydrogen into helium requires neutrons to be created through proton to neutron conversions. Fission of uranium or plutonium releases free neutrons that trigger further fission events in a chain reaction. The neutron's ability to transform between its free and bound states, to decay and to be captured, to be created and destroyed, is fundamental to how nuclear energy works. There's something deeply elegant about all of this. The same particle, the neutron, can be stable or unstable depending on its environment. Not because the particle itself changes, but because the definition of downhill changes. In empty space, downhill means decaying into a proton, electron, and antineutrino. Inside a stable nucleus, there is no downhill. The neutron sits in a valley. The decay that was inevitable in isolation becomes impossible in community. The laws of physics don't change between these two situations. The same forces are at work. The same quantum mechanical rules apply. The same conservation laws hold. What changes is the context, the energy landscape, the set of available states. And that change in context is enough to flip the neutron's fate from certain death to effective immortality. This teaches us something profound about how nature works. Stability is not an intrinsic property of a particle. It's a relational property. It depends on the particle's relationship to its surroundings, to the other particles it's bound with, to the energy levels available, to the overall energy of the system. A neutron isn't born stable or unstable. It becomes stable or unstable depending on where it ends up. If it's captured into a tightly bound nucleus, it lives. If it remains alone, it dies. The particle itself hasn't changed. Its destiny has. And this raises a question that takes us even further. What happens in the most extreme environments imaginable? What about neutron stars, where matter is compressed to densities beyond anything found in ordinary atomic nuclei? In a neutron star, neutrons are packed together so tightly that the distinction between individual nuclei breaks down entirely. It's not individual atoms with nuclei and electron clouds anymore. It's a sea of neutrons, with smaller populations of protons and electrons mixed in, all compressed into a ball perhaps 12 miles across, but containing more mass than the sun. In this environment, a completely new mechanism keeps neutrons stable, a mechanism that has nothing to do with nuclear binding energy as we've described it. It has to do with the Pauli exclusion principle applied not within a nucleus but across an entire star. And understanding how that works reveals yet another layer of the neutron's remarkable story, one that connects the quantum physics of the very small to the astrophysics of the very large in a way that is as beautiful as it is unexpected. We've seen how nuclear binding energy can save a neutron from its fate. Inside a stable nucleus, the energy landscape changes, the downhill path to decay disappears, and the neutron endures. But now, let's travel to a place where matter exists under conditions so extreme that ordinary nuclei can't even form. A place where the density is so high that individual atoms are crushed out of existence, where protons and neutrons aren't organized into neat little nuclei surrounded by electron clouds, but are instead packed together in a single continuous mass, stretching for miles. A place where gravity has squeezed matter to the breaking point and beyond. We're going to a neutron star. And what happens to neutrons there reveals an entirely different mechanism of stability. One that connects the smallest scales of quantum mechanics to the largest scales of astrophysics in a way that is breathtaking. A neutron star is born in violence. When a massive star, roughly 8 to 25 times the mass of our Sun, reaches the end of its life, it has burned through its nuclear fuel in progressively faster fusion stages. Hydrogen fuses to helium over millions of years, helium to carbon over hundreds of thousands, carbon to neon, neon to oxygen, oxygen to silicon, each stage faster than the last. Silicon fusing to iron takes only about 1 day, and then fusion stops. Iron is the end of the line. Fusing iron absorbs energy rather than releasing it. The iron core can no longer generate the outward pressure needed to support the star above it. In a fraction of a second, the core collapses. The outer layers fall inward at speeds approaching a quarter of the speed of light, slam into the collapsing core and bounce off, creating a shock wave that tears the star apart in a supernova explosion. But the core doesn't get destroyed in the explosion. It gets compressed. The collapse drives the density so high that atoms as we know them cease to exist. Electrons are forced into protons through a process called inverse beta decay, or electron capture. This is essentially the reverse of the neutron's beta decay. Instead of a neutron emitting an electron and becoming a proton absorbs an electron and becomes a neutron, emitting a neutrino in the process. During the core collapse, this happens on a massive scale. Trillions upon trillions of protons absorb electrons and become neutrons. The neutrinos produced carry away enormous amounts of energy. In fact, about 99% of the energy released in a supernova is carried away by neutrinos, not by light or the kinetic energy of the explosion. The burst of neutrinos from a supernova is so intense that even though neutrinos barely interact with matter, the sheer number of them helps drive the shockwave that blows the star apart. What's left behind after this catastrophic compression is a neutron star. It typically has a mass between about 1.4 and 2 times the mass of our Sun, compressed into a sphere roughly 20 kilometers across. That's about the size of a city. Imagine taking something more massive than the Sun and squeezing it until it fits inside the boundaries of a small metropolitan area. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. That's roughly the weight of a mountain, compressed into a volume smaller than a sugar cube. At the surface, the gravitational pull is about 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you'd be flattened into a layer of atoms thinner than a sheet of paper in less than a microsecond. Inside this incredibly dense object, matter exists in a state found nowhere else in the ordinary universe. The outer crust of a neutron star is made of extremely neutron-rich nuclei, exotic isotopes that couldn't exist under normal conditions, arranged in a crystalline lattice and surrounded by a sea of free electrons. As you go deeper, the nuclei get larger and more neutron-rich. Eventually, at a depth of perhaps a kilometer or so, the nuclei become so swollen with neutrons that neutrons begin to drip out of them. This is called the neutron drip line. Below this point, you have a mixture of enormous neutron-rich nuclei, free neutrons and electrons, all packed together under immense pressure. Deeper still, the individual nuclei dissolve entirely. The distinction between one nucleus and another breaks down. What you're left with is a continuous fluid of neutrons, with a small admixture of protons and electrons, roughly 5 to 10% each. This is the bulk interior of the neutron star, and it's here that the neutron stability question gets truly fascinating. In this environment, the neutrons are not bound inside individual nuclei. There are no nuclei. The neutrons are free, or rather, they exist in a continuous dense fluid. By the logic we established earlier, free neutrons should decay. They should undergo beta decay, transforming into protons, electrons, and antineutrinos. A free neutron in empty space decays in about 10 minutes. So why doesn't a neutron star evaporate in 10 minutes as all its neutrons decay away? The answer lies in the Pauli exclusion principle, the same quantum mechanical rule we discussed for nuclear energy levels, but now applied on a vastly larger scale. Remember, the Pauli exclusion principle says that no two identical fermions can occupy the same quantum state. Neutrons are fermions, protons are fermions, electrons are fermions. In a neutron star, all three types of particles are packed together at extraordinary densities, and at these densities, the available quantum states get filled up. Think of it like filling a theater from the front row to the back. The first neutrons settle into the lowest energy states. Then the next neutrons take slightly higher energy states. Then higher still. With roughly 10 to the power of 57 neutrons in a typical neutron star, an enormous number of quantum states are filled. The highest occupied energy level, the level where the last neutrons are sitting, is extremely high. Physicists call this the Fermi energy. In a neutron star, the Fermi energy of the neutrons can reach tens to well over 100 mega-electron volts. Now, here's why this prevents beta decay. When a neutron decays, it produces a proton and an electron. Those products must go somewhere. They must occupy available quantum states. But in a neutron star, the protons and electrons also form degenerate Cs with their own Fermi energies. The proton states are filled up to the proton Fermi level. The electron states are filled up to the electron Fermi level. For a neutron to decay, the resulting proton must find an available proton state, and the resulting electron must find an available electron state. But all the low energy states are already taken. The new proton and electron would have to be created at energy levels above their respective Fermi surfaces. And here's the critical point. Creating a proton and electron at those high energy levels costs energy. More energy than the neutron-proton mass difference provides. The neutron's mass surplus of 1.293 megaelectronvolts, which was more than enough to power beta decay in empty space, is utterly insignificant compared to the Fermi energies in a neutron star. The energy cost of placing the decay products into available quantum states far exceeds the energy gain from the mass difference. The decay is energetically forbidden, not because of nuclear binding energy, as in an atomic nucleus, but because quantum statistics have filled up all the low energy states for the decay products. There is literally nowhere for the proton and electron to go that wouldn't cost more energy than the decay releases. This is called Pauli blocking, and it's one of the most elegant examples of quantum mechanics operating on macroscopic scales. A principle that governs the behavior of individual particles, the exclusion principle, is responsible for the stability of an object 20 kilometers across containing more mass than the Sun. Without Pauli blocking, neutron stars couldn't exist. The neutrons would decay, the star would lose its neutrons, and the entire structure would collapse or transform into something else entirely. The Pauli exclusion principle holds the neutron star up in two ways. It prevents the neutrons from decaying, and it also provides a pressure, called degeneracy pressure, that resists gravitational collapse. Even at absolute zero temperature, with no thermal energy at all, the fermions in a neutron star would still exert pressure simply because they cannot all occupy the same quantum state. They're forced into higher and higher energy levels, and that creates a pressure that pushes back against gravity. Inside a neutron star, there's actually an equilibrium between beta decay and its reverse, electron capture. A small number of decays and reverse decays happen constantly, maintaining a balance. If a neutron decays, producing a proton and electron that squeeze into barely available states at the top of the Fermi sea, the reverse process almost immediately occurs. A proton captures a high-energy electron and turns back into a neutron. The two processes balance each other, maintaining a constant ratio of neutrons to protons. This equilibrium is called beta equilibrium, and it determines the exact composition of the neutron star's interior. The result is a mixture that's roughly 90 to 95% neutrons and 5 to 10% protons and electrons, with the exact ratio depending on the density and the properties of the strong force at these extreme conditions. The interior of a neutron star is also thought to contain exotic states of matter that don't exist anywhere else. At the very highest densities near the core, the neutrons themselves might break down. The quarks inside the neutrons could become deconfined, meaning they're no longer locked inside individual neutrons, but instead flow freely in a quark-gluon plasma. This hypothetical state is called quark matter, and whether it actually exists inside neutron stars is one of the biggest open questions in nuclear physics and astrophysics. If quark matter forms, the simple picture of neutrons and protons breaks down entirely. You no longer have neutrons that can decay or not decay. You have a soup of up quarks, down quarks, and strange quarks interacting through the strong force in ways we don't fully understand. Some theoretical models predict that the quarks could pair up in exotic ways, forming a color superconductor, a state of matter where quarks form pairs analogous to the electron pairs in a superconductor, flowing without resistance. These are speculative ideas, and we don't have the experimental tools to test them directly. But the equations of quantum chromodynamics, the theory of the strong force, allow for these possibilities, and neutron stars are the only places in the modern universe where conditions might be extreme enough for them to occur. Recent observations have given us new tools to study neutron star interiors. In 2017, gravitational wave detectors observed the merger of two neutron stars for the first time, an event called GW170817. This merger was also observed with telescopes across the electromagnetic spectrum, from gamma rays to radio waves. The data from this event provided constraints on the equation of state of neutron star matter, essentially telling us how matter behaves at these extreme densities. These observations have ruled out some theoretical models and supported others, narrowing down the possibilities for what the interior of a neutron star actually looks like. More observations of neutron star mergers, expected in the coming decades as gravitational wave detectors become more sensitive, will continue to refine our understanding. Pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, have also provided valuable data. By precisely timing the radio pulses from pulsars, astronomers can measure the mass and radius of neutron stars with remarkable accuracy. These measurements constrain the equation of state and help determine whether exotic states like quark matter exist in neutron star cores. Let's step back now and look at the bigger picture. We've explored three different environments for neutrons. A free neutron in empty space, which decays in about 10 minutes because its mass exceeds that of its decay products and nothing prevents the transformation. A neutron inside a stable atomic nucleus, which can endure for billions of years because nuclear binding energy reshapes the energy landscape, making beta decay energetically unfavorable. And a neutron inside a neutron star, which is stabilized not by nuclear binding but by the Pauli exclusion principle, which blocks beta decay by filling up all the available quantum states for the decay products. Three environments, three different stability mechanisms, one particle. The neutron doesn't change between these settings. Its quarks are the same. Its mass is the same. The weak force operates the same way. What changes is the context, the energy landscape, the available states, and that context determines everything. This leads us to a deeper truth about how the universe is built. The neutron's instability isn't a flaw. It's not a mistake in the design of matter. It's a feature that has consequences rippling across the entire structure of the physical world. That tiny mass difference of 1.293 mega electron volts between the neutron and the proton, the one that dooms the free neutron, is the same mass difference that powers a vast array of processes essential to the universe as we know it. Beta decay, the process that destroys free neutrons, is the same process that drives radioactive decay in unstable nuclei. And radioactive decay isn't just a curiosity, it's what heats the interior of the Earth. The decay of uranium, thorium, and potassium isotopes in Earth's mantle and crust generates roughly half of the planet's internal heat. This heat drives plate tectonics, volcanic activity, and the convection currents in Earth's liquid iron core that generate our planet's magnetic field. Without radioactive decay, Earth's interior would have cooled long ago. The magnetic field might have weakened and disappeared. Without the magnetic field, the solar wind would strip away Earth's atmosphere, much as it stripped away Mars's atmosphere when Mars lost its magnetic field. Life on Earth might never have developed, or it might have been limited to subsurface environments protected from radiation. The neutron's instability, operating through the beta decay of radioactive isotopes, helps keep our planet geologically alive. The neutron lifetime also played a critical role in the first few minutes after the Big Bang. During Big Bang nucleosynthesis, the period roughly 1 second to 20 minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to occur. Free neutrons and protons existed in roughly equal numbers at very early times. But as the universe cooled, the balance shifted. Neutrons are heavier than protons, so at lower temperatures, the equilibrium favors protons. By the time nuclear reactions began in earnest, there were roughly 7 protons for every neutron. These neutrons were free, floating in the hot plasma, and they were decaying. Every 10 minutes, half the remaining free neutrons transformed into protons. This set a clock. If nuclear reactions had taken too long to start, all the neutrons would have decayed away, and the universe would contain nothing but hydrogen. No helium. No elements heavier than hydrogen. But nuclear reactions started fast enough to capture most of the remaining neutrons into helium-4 nuclei before they could decay. The result was a universe that was roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. This prediction, made by the theory of Big Bang nucleosynthesis, matches observations of the primordial abundances of these elements with remarkable precision. It's one of the strongest pieces of evidence for the Big Bang model, and the specific abundances depend sensitively on the neutron's lifetime. If the neutron decayed faster, fewer neutrons would survive to be captured into helium, and the universe would have less helium. If the neutron decayed slower, more neutrons would survive, and the universe would have more helium. The observed helium abundance matches what you'd expect for a neutron half-life of about 10 minutes and 14 seconds, precisely what we measure in laboratories. The neutron's instability isn't just a subatomic curiosity, it determined the chemical composition of the entire universe. Inside stars, the interplay between neutrons, protons, and beta decay continues to shape the elements. The process of stellar nucleosynthesis, the fusion reactions in the cores of stars that build heavier elements from lighter ones, involves neutrons at many stages. In massive stars, during the late stages of their lives, neutrons are produced in various reactions and captured by existing nuclei. This neutron capture, followed by beta decay, is how many of the elements heavier than iron are built. There are 2 main pathways. The slow neutron capture process, called the S process, occurs in certain giant stars over thousands of years. Nuclei capture neutrons one at a time, and between captures, unstable nuclei have time to undergo beta decay, transforming neutrons into protons and moving the nucleus to a higher element on the periodic table. The rapid neutron capture process, called the R process, occurs in extreme environments like neutron star mergers and certain supernovae, where the flux of neutrons is so intense that nuclei capture many neutrons in quick succession before any beta decay can occur. This creates extremely neutron-rich nuclei that then undergo a cascade of beta decays, transforming excess neutrons into protons and producing the heaviest elements in nature, including gold, platinum, and uranium. Every gold atom in existence was likely forged through the R process, probably in a neutron star merger. Two neutron stars spiraling together, colliding, ejecting neutron-rich matter into space. That matter, suddenly freed from the extreme conditions of the neutron star, underwent rapid nuclear reactions. Neutrons were captured by seed nuclei. Beta decays transformed neutrons into protons. The result was a spray of heavy elements, including gold, flung across space. Eventually, that material was incorporated into new stars and planets. The gold in a ring on your finger was made in the collision of two dead stars, through a process that depended on the neutron's ability to undergo beta decay, the same instability that prevents a free neutron from surviving alone. The universe builds complexity from instability. The neutron's tendency to decay is not a weakness. It's the engine that drives the creation of heavy elements. There's a remarkable chain of reasoning here that connects the tiniest details of subatomic physics to the largest features of the observable universe. The mass of the up quark and the mass of the down quark determine the mass difference between the neutron and the proton. That mass difference determines whether free neutrons are stable or unstable. The instability of free neutrons, combined with the specific timescale of their decay, determined the helium abundance in the early universe. The existence of helium and other light elements provided the fuel for stellar fusion, which powered the first stars. Those stars built heavier elements through fusion and neutron capture. When massive stars died, they scattered those elements into space, including the neutrons trapped in their cores, which were released in supernova explosions and neutron star mergers. Those scattered elements became the raw material for new stars, planets, and eventually life. Every step in this chain depends on the neutron being unstable in isolation, but stabilizable in the right environment. Every step depends on that tiny mass difference, 1.293 mega electron volts, being exactly what it is. Not zero, not too large, not reversed, just right. And yet this mass difference isn't determined by any single simple principle. It emerges from a complex interplay between the strong force, the electromagnetic force, and the masses of the quarks, themselves determined by the quark's interaction with the Higgs field. It's a number that falls out of the equations of the standard model of particle physics, but it's not a number that anyone predicted ahead of time. It's measured, not derived from first principles. We can calculate it using lattice quantum chromodynamics, sophisticated computer simulations of the strong force, and those calculations agree with measurements. But the calculation requires knowing the quark masses and the strength of the forces as inputs. We don't have a deeper theory that explains why the quark masses are what they are or why the forces have the strengths they do. Those are just the values our universe happens to have. They might be different in other regions of a multiverse if such a thing exists. They might be set by some deeper principle we haven't discovered yet. Or they might be truly fundamental, brute facts about reality that have no deeper explanation. We don't know. What we do know is that these values, whatever their origin, conspire to create a universe of extraordinary complexity. A universe where neutrons can exist stably inside nuclei, but not outside them. Where the interplay between stability and instability drives the creation of elements, the generation of heat inside planets, and the conditions for life. Where a particle that decays in 10 minutes when alone can endure for billions of years when bound, and can persist indefinitely when compressed into the heart of a dead star. There's something almost poetic about the neutron's predicament. It's a particle that cannot exist alone. In isolation, it's doomed by the tiniest imaginable margin of mass. But in community, surrounded by other particles, bound by forces that reshape the energy landscape around it, it can endure effectively forever. The same particle, the same quarks, the same mass, but a completely different destiny depending on whether it's alone or part of something larger. Perhaps that's the deepest lesson of the neutron story. Survival isn't just about what you are, it's about where you are. It's about context. The relationships between a particle and its neighbors, the forces that bind them, the quantum mechanical rules that govern what transitions are allowed and forbidden. All of these external factors determine whether a neutron lives or dies. The neutron itself is the same in every case. It carries the same quarks, the same gluon field, the same tiny surplus of mass. But that surplus, that gentle slope toward decay, can be neutralized or even reversed by the right environment. Strip away the environment, leave the neutron truly alone, and that gentle slope becomes inevitable. The neutron rolls downhill, transforms, and is gone. Every neutron inside your body right now is billions of years old. It was forged in a star, survived a supernova, drifted through space as part of an atom, was incorporated into the cloud of gas and dust that formed the solar system, became part of the Earth, and eventually became part of you. Through all of that journey, through all those billions of years, it remained stable because it was never alone. It was always part of a nucleus, always surrounded by other particles, always sitting in an energy valley from which beta decay was forbidden. If at any point along that journey it had been knocked free, stripped from its nucleus and left alone in empty space, it would have had about 10 minutes to live. 10 minutes, and then it would have become a proton, an electron, and an antineutrino, scattered to the void. But it wasn't knocked free. It stayed bound. And because it stayed bound, it survived long enough to become part of you. You are, in a very real sense, built from particles that can only exist because they found each other. Neutrons that would have perished alone found stability in community, inside nuclei, inside atoms, inside molecules, inside the cells of your body. The matter that makes you possible is matter that depends on togetherness for its very survival. The universe is built on balances like this: tiny mass differences, delicate energy margins, quantum rules that permit one outcome and forbid another, forces that compete and cooperate in ways that produce either permanence or transformation, depending on the circumstances. The neutron story is just one thread in this tapestry, but it's a thread that touches everything. It touches the structure of atoms, the power of stars, the creation of elements, the heat inside planets, the chemistry of life. Pull on this one thread, change the neutron's mass by a fraction of a percent, and the entire tapestry unravels. The elements change, the stars burn differently. The chemistry of life may become impossible. We live in a universe where a particle can be immortal or doomed, depending solely on whether it has neighbors. Where 1.293 mega electron volts, a mass difference barely larger than the mass of 2 electrons, determines whether matter is stable or falls apart. Where the same physical laws produce both permanence and transformation, both stability and decay, depending on context alone. And that ultimately is why neutrons can't survive alone. Not because they're broken, not because they're defective, not because there's something wrong with them, but because the universe, through the precise values of its fundamental constants, has made the neutron just barely heavier than the combination of particles it can become. In isolation, that tiny margin is everything. It's the slope that the neutron rolls down, slowly, reluctantly, over the course of about 10 minutes. But in the right company, surrounded by the right particles, bound by the right forces, that slope vanishes. The neutron finds stability not within itself, but in its relationship to everything around it. Alone, it has 10 minutes. Together, it has forever. And the universe, with all its atoms, all its elements, all its stars and planets and the life that populates at least one small world, exists because of exactly that difference.